Good morning, everyone. Welcome to Brainome's second Cortec webinar. This is Cortec 201, where Dr. Gerald Friedland, our CTO, is going to do a deep dive into the math and algorithms behind what's going on with Brainome's Dimensions product. We're in the middle of two webinar series that are going on in parallel. We're here at Cortec 201, which is the second of three in the Cortec series. We're also working our way through 6 series sessions of benefits and applications of using dimensions. And the next one is Thursday, and it's going to be about finding the needle in the haystack. You can sign up for and learn about more details about all of these webinars at the URL here at the bottom, which is at brainome.ai, our website, on the resources page under events. Now I'd like to introduce to you Gerald Friedland. If you haven't met him or heard him speak already, you're in for a treat. Gerald is CTO at Brainome. He's also teaching as an adjunct professor in the Electrical Engineering and Computer Sciences Department at UC Berkeley. Before having that appointment, he was at Lawrence Livermore National Lab, and prior to that, at the International Computer Science Institute in Berkeley. His work over the years has focused on signal processing and machine learning. He's published more than 250 peer-reviewed articles in conferences and journals, and he's published 3 books. Dr. Friedland received his doctorate, summa cum laude, in computer science from the Free University in Berlin in 2006. I'll also invite you, as Gerald is speaking, to put your questions into the Q&A channel, and we'll certainly have plenty of time for Q&A and interactive discussion with Gerald at the end of the presentation. All right, Gerald, take it away.
Okay. Thank you very much, Lynn, for the kind introduction, and also thank you everybody for coming in. So this session is actually going to be a real sort of theoretic session as much as, do it for a general audience. And so as that part, I would like everybody, like if you have questions, to just answer questions right away. It's dense material, but the slides are going to be online, and also the presentation is going to be online. And also, I'm always open for question. You can definitely just randomly, email me a question. That's not something new for me at all. Okay, please go ahead and do that. So, so we're gonna do a deep dive, as much as we can do in 30 minutes, into how Brainome actually measures data to help model building. And one of the major points here is the memory equivalent capacity. If you were in the 101 seminar, you know that this is one of our major sort of cornerstones. We also will talk about generalization, and with it comes overfit detection, and with that it comes attribute ranking, which is interesting because that may not be something that follows naturally like on first glance, but it does follow naturally once we go through the math. So before we go in any math, we have to start with philosophy, and that's usually how many things start. So somewhere in school, somewhere in college, somewhere, maybe on TV, you might have seen a formalism that's called the scientific method. And of course, that's something humans have been doing, and even animals have been doing very naturally, right? So you have some observation, you see something, and you're curious about it. So now what happens is that as you're curious about something, you want to know more, right? So, and the most prominent example, obviously, is Newton sitting under a tree and the apple falling on his head, right? So as the apple fell on his head, there was an observation, pretty brutally, ouch, right? And so now his question was, A, why does the apple fall from the tree? But also, does the apple fall from the tree faster, slower? Is it more ouch or less ouch, depending on the height of the apple or on the size of the apple? And in order to figure that out, what you have to do is you have to do experiments, right? In the beginning, you don't know anything. The first thing you have to do is to just do empirical observations. Now, these empirical observations, if you have enough of them, will somehow magically lead you to a theory. Okay, so it turns out, by Newton varying the height and the the size, or actually the mass of the apple, he came up with E equals mgh, sort of the potential energy formula, and also other principles like action and reaction and so on and so forth. Now, the trick here is, why do we want sort of these rules, right? So we have now rules that say, well, the kinetic energy of the apple is E equals m times g times h. Well, it's because now I don't have to, have apples. I don't have to do experiments anymore. I don't have to, anymore go and measure apples falling from trees. All I have to do is use the formula, and it'll predict exactly how the apple will fall under, the circumstances that we have. We should also outline here that this is a point-sized apple falling in a vacuum, right? And so obviously, if you throw the apple from an airplane, which Newton didn't have available, it's actually not going to work, the formula, because you reach terminal velocity, for example. Okay, so it's always bound to the inference you can do is always bound to the experiments that you're doing. And now, this was Newton, obviously hundreds of years ago. The question is, what's new here? Why am I telling you this today? Well, what's new here is that in the 50s and 60s, we figured out we have computers. Okay, I mean, computers were invented earlier, but really in the 50s and 60s, we figured out when there are experiments that are hard to conduct. For example, nuclear explosions that basically have huge economical impact and a huge political impact and all kinds of problems. It would be kind of nice to not have to do experiments, but maybe to just theorize a prediction and then do a simulation, and based on the observation, see if that makes sense with everything. And that was called simulation. So since about the 50s and 60s, a lot of science is using computers for simulation of all kinds of sorts. Now, what's really new though, and that's kind of came in the 2000s, and probably just basically in the last 10 years, is not that part anymore where we try to have a theory and then simulate and see if that observation fits the theory, but the part where we actually go and say, no, I'm just going to put my observations into the computer, and then I call it machine learning, and then the predictions come out. So the interesting part here is that, of course, now the machine learning is redoing the theory building, right? So we have this deep learner, a big deep network that does all, I mean, all of kind of interesting things. Yeah, it's funny because we don't understand what it does, because yeah, it contains the theory, right? And that's obviously a problem right there. Having said that, we know a lot from philosophy on how to build theory by hand, right? There's stuff, for example, like Occam's razor. So if we know a lot from theory and how to build stuff by hand, why don't we apply this to machine learning? And in fact, by doing so, we can formalize it a little more, and basically go ahead and say, okay, let's figure out how Occam's razor actually behaves if we formalized it, and all of these kind of things. And I call this data science. Okay, for me, data science is the science of automating the scientific method, right? Because we get into the point here where machine learning is building the theory and gives us the prediction, rather than a human coming up with a formula. And let's formalize this a little bit. So what happens here is, when we do the scientific method traditionally, is you have a person that measures it, they put the measurements into a table. The table typically looks like this. You have some input variables, and then in the last final column on the output, you have an output variable. So for example, it could be the height and the mass of the apple. And then the output variable is obviously maybe measured as the amount of pain it induces on somebody's head or something, right? Or obviously, if you be more scientific about it, we could measure, force or something like that. So ultimately, the point is, you have some input variables, then you conduct the experiment, and you get a target column. And if you collect enough data, and maybe some smart person sits at it and says, "Ha, I find the pattern to predict from the input to the output, and it's E equals mc squared," right? So, and then if that is a really surprising prediction, then we call this person genius. Okay, that's just what was traditionally what happened. Now, actually, nothing changed, except instead of the brain, the genius brain, we are trying to make this thing automatic, and we're trying to have Einstein be replaced by a finite state machine, really, because it's a computer doing this, maybe a big computer, But the point is, it's a finite state machine. That's all it is. And so now the question becomes, hmm, what can we say about the finite state machine? Trying to learn the data. When is it actually learning the data well? When is it actually coming up with something useful? And the first thing we'll observe, by the way, is that a formula like this, E equals mc squared, doesn't have a lot of variables. In fact, this thing only has one variable, the mass, right? C squared is even a constant, right? So if you just want to count characters, then you see 3. But reality, there's not a lot of parameters. Um, and that makes it very general, and it also makes it, somewhat surprising. Now, we could ask the same thing. We could go and say, well, let's start with Occam's razor, and we actually want a formula out, right? We want something prediction that we understand because we ask the computer to do theory building. And so my thought framework of machine learning is that we assume we have a bunch of input variables. They could all be real variables, right? In computers, there never are, but it doesn't matter. We just assume they're real value, and then you have a target function which is sort of your outcome. And for simplicity and for this presentation, we will say the outcome is only yes or no, head or tail, 0 1. It's a binary balanced outcome. And so now the question is, okay, so if I now take this table with all my data and I try to convert this table into a finite state machine with the least amount of states, well, first of all, what would be the least amount of states, but also what, how does a conversion even work, right? So first thing we can figure out, okay, if I was drawing the finite state machine, the simplest finite state machine is actually given by the table itself, which is you have your input and then you draw an arrow to the output. You have another input and you draw an arrow to your output, which basically is a lookup table. It's your table itself is a lookup table because if you had the exact same inputs again, you should get the exact same output again, right? And so that means that the number of rows in your lookup table is right there the maximum number of state transitions that you should need in your finite state machine. Because as you go, each row gives you a perfect prediction. The problem here is um, we want more, right? We want to have the table be representative such that if there's something coming in that we haven't experimented yet, it is not perfectly fitting the table, we can predict that too, and hopefully correctly. And so now the question is, would we need more state transitions for that or less state transitions for that? And obviously, first of all, the maximum is the number of rows. So it gives us a lookup table. Then it makes total sense to say, yeah, we need less for that, because what happens is then each state transition can take more than one output. So more than one input and get to the same output. Basically, we're using redundancies. We're finding patterns. And now the question is, minimally, how many state transitions would we need? And that is actually not an easy question to answer. But again, we can be engineers about it and say, first of all, we know a maximum. And then secondly, we can go from there and try to reduce and reduce and reduce and see where we go. And so ultimately, um, so we will say the following. Memorization is, if we can't deduce, all we can do is memorize the observations verbatim, right? So as I said in the one-on-one seminar, if you have 2, 4, 6, 8, 10, you immediately know you deduce +2 as a rule, you're done. If you have 6, 5, 1, 3, you deduce nothing, and it be just basically all you can do is memorize. So same here, if we memorize the table, all we can do is memorize the observations verbatim. And that we call, in traditional machine learning lingo, overfitting. Because what happens is that each variable just exactly memorizes what's going on. No variable can take up more than one input particularly. That means there's no generalization. And so that makes it automatic that we can say generalization is guaranteed to happen when we reduce the parameters below the memorization capacity. That means when we use less state transitions in our finite state machine, that would need it, then would need it for a lookup table. In the best case, and if you do it good enough, it will make the machine learner forget what's not relevant, right, with the target function, because ultimately it'll just sort of store, and we could even almost call them the support vectors, right? Those values that really matter, and then everything that's close will be automatically inferred. And again, that leads us again to this notion that we explained last webinar, which is memorization is worst case generalization. Memorization just doesn't generalize. Memorization generalizes only basically to these values you already have stored. So that's not the generalization. You would do really poorly on unseen variables. So to get to a little bit more math, the interesting part is while it's very hard to talk about generalization, it is very easy to talk about memorization. So let's start with that. And we have something arithmetic that anybody who does computer science sort of has to do in and out in their freshman years. And I'm just going to repeat a little bit, and it's something that's interesting to know. So it's all about the logarithm, okay? And we do a log base too, because in a computer, everything is binary. So information is reduction of uncertainty. That's first of all, the number one, you know, sort of definition here. So what this means is that yes, the information H is by default, first of all, just uh, the log2 of the number of states. But since it's reduction of uncertainty, it is also equivalent just by logarithm rules with minus log2 1 divided by the number of states, which is just the probable, if all the states are equiprobable, that is just the probability of encountering a particular state. And the funny thing here is that Shannon told us, yeah, and we call that bits, right? So if you had two states, heads and tails, it would be 1 divided by 2, and minus log2 of that is 1, which gives you 1 bit of information. So before I know the outcome of the coin flip, I have 1 bit of uncertainty. And then the moment the coin flip happens and I can observe the outcome, I have no more bits of uncertainty, but this is because 1 bit of information reduced the minus 1 bit of uncertainty. And I'm thinking this way, and I kind of like to formalize it sometimes this way. This is people do this differently, mostly in mainstream, but there is a growing community of people that says actually we should not have that negative sign in front of the log, because really it's like this: if you have $100 on your bank account, you have $100. If you have minus $100 on your bank account, well, you have $100 of debt. And basically, you can kill that debt by putting in $100 again, you get to zero. And it's the same behavior that we have for information. So basically, uncertainty should just be the log2 of the probability, or the log2 of the 1 divided by the number of states, because then you get to negative bits. So you can actually measure uncertainty in negative bits, which is very interesting, because usually you think, oh, I don't know anything. How could I measure this? No, you can, because information is reduction of uncertainty, and everybody agrees you can measure information. So this is, by the way, only valid right here if the states are all equiprobable. But if these states are not equiprobable, then we have the Shannon entropy. And I'm not going to go into this detail, but even then, you can go to the expected number of bits that are uncertain, or the expected number of bits that you need to encode something. So with all this framework in mind, that's sort of the information theory, I will skip over to something a lot deeper that I actually cannot completely explain here given the time. But basically we get to the point where you could use that Shannon information theory to understand machine learning. And this was not my invention. In fact, Thomas Cover did a lot of work in the 60s, and he came up with really important theorems. But then there's a very good book that I recommend everybody. It's from David McKay, Information Theory, Inference, and Learning. And in his chapter 40, he asked himself, okay, can we basically solve that very old question of why can a single perceptron not model all uh, Boolean functions of two variables? And he does it, and again, I can't go into deep, by putting the perceptron into Shannon's information channel, right? Just as a quick reminder, Shannon's information channel is basically saying, okay, a sender wants to send a message. It goes to an encoder, because the encoder does something with it. That becomes a signal. Then it goes through a channel, and there may be some loss, and you get some signal prime. And now as you have, signal prime, which is kind of a lossy signal, we want a decoder such that we get a message prime. And the message prime obviously should be the original message again. So the question in a mathematical sense is, how do I have to build the system such that message equals message prime in the end, given various parameters of encoder and channel? And now McKay asked the same questions. He said, okay, in a machine learning scenario, our messages are the labels, right? The labels are cat dog. That's what I actually want to do correctly. But and then what we do is we have this training data that's sort of external, and the encoder is nothing else but our training learning method. And so what we do is we go and say, let's take a neural network, for example, and give it labels and data, and then the neural network will encode, the labels and data into weights, right? These are the parameters that we train as, it's sort of in the neural network. And then we send that over a channel that doesn't matter, so it's identity channel. But then the question is, once I have the data again and the weights, can I actually reproduce the original labels? And what you see here is, again, we're not talking about generalization yet. We're talking about memorization, and the fact that actually when can we memorize a function with, a certain learning algorithm. And so um, that is basically where we came from. And then from that, we derived, and that's a paper that we should send the reference after the webinar. We derived what we call the memory equivalent capacity. And that means I can guarantee you that if you have n rows in a table of a binary classification task, that these n rows can be memorized by any machine learner that has n bits of memory equivalent capacity. Okay, because again, this is assuming balanced binary. Then balanced binary means that each row has one bit of information. And if you have n bits of memory equivalent capacity, then that machine learner can absolutely memorize this data. And again, we're still talking about memorization. And so McKay solved it by looking at something which was kind of surprising. The perceptron itself, by the way, has been invented twice and kind of at the same time, which is nothing else but sort of the neuron that we use today. And also, it is actually a quite um, accurate abstraction of a biological neuron. The biological neuron is nothing else but an energy threshold. Okay, you don't think about your left pinky toe right now. I mean, right now you do because I talk about your left pinky toe, but usually you only think about your left pinky toe if somebody steps on it or if you step on something, and that's the idea of a neuron. It actually makes you ignore signals unless they're high enough threshold. And so the perceptron itself has been described by Rosenblatt in a very interesting paper that, by the way, references a lot of information theory, and later on that was just ignored. And then Vidro did something else. He built an electric component that was basically an energy threshold. So a transistor is a signal threshold, right? So if there's enough voltage or current on your base, then the transistor switches through. And he wanted to build something where if there's enough energy at the base, the element will switch through. And it was called Adaline. But the major point is it's basically a parallel invention of the perceptron, and this led to sort of the idea of having perceptrons and neurons being physical um, physical things that can be interpreted as elements in an electrical circuit. Now, McKay, however, goes and says, well, here's what's interesting. If we have he just goes math and he says, if we have a dot product like we have in a perceptron, then we actually know everything about how many separations, linear separations, can be made in space, because that was found by a guy called Schläfli in 1852. There's a Swiss guy, Swiss high school teacher, who basically decided, oh, I'm gonna solve a bunch of things with algebra and geometry, and he basically created, showed people that algebra also is consistent with geometry, and one of these things was and he created a function that tells us for how many thresholds in k dimensions can be created for n distinct points in general positions. And that is exactly the question that we have to answer for the perceptron. And I can't go into too much detail about this function. We could spend a whole webinar on that. But what I did is, let's not go so complicated. If we take the log 2 of those numbers that you see here, right? Then you will see that, yeah. So what happens is, what happens is if you have four points, right? Then there's obviously all the functions you can create from that is just 16, 2 to the power of 4. Well, and that's interesting because if you have 4 points and 4 parameters, that means, yeah, you're done, right? There's not more that can be done. That's if you go this way. But let's say you have 4 points, like in all the binary functions of, um, sorry, if you have 4 points like in 2 input variables for binary function, right? x1, x2, 0, 0, 0, 1, 1, 0, 1, 1, then you would have 16 functions of that. And it turns out with a single perceptron where you only have 3 parameters, which is the weight 1, the weight 2, and the bias, you only have 14 that you can actually model. And that's a little bit of a problem because that means XOR and not XOR cannot be modeled. And the interesting part here is that solved Minsky's question. But I don't want to think so complicated. We just go take a step back and say, well, what if we took the log2 of this number, right? The log2 of this number works because the log2 of 16 is 4, right? It tells us, okay, my memory equivalent capacity is 4, I can do it. But the log2 of 14 is 3 point something. And that means I cannot guarantee that all the functions can be modeled. And that's how simple that is. So we can basically say n bits in the model can maximally model n bits of outcomes. And that's the pigeonhole principle, universal lossless. All of this is also true, right? But the point is, by just measuring the number of, so basically taking that function and just taking the log2 of that, we get a bit measurement, which we call memory equivalent capacity. And using that memory equivalent capacity, we can now guarantee that, n rows in sort of a balanced binary table can be memorized or not. That's the simple trick about that. Okay. So now, however, this was only valid for the single perceptron. We also had to take Vidro's interpretation of perceptrons being electrical circuits and create 4 rules. These are all published, by the way. Again, you can Google that. And it turns out, actually, you just treat them as elements in a circuit. So this is how you get to the memory equivalent capacity of an entire neural network. This doesn't include convolution networks and these kind of things. Okay, this is just for regular decision networks. Now, the output of a perceptron is maximally 1 bit. That's easy to see because it fires or it doesn't fire. And the you get 1 bit if it fires in 50% chance or or not in 50% chance. That's 50-50 chance gives you 1 bit. Any other distribution gives you less than 1 bit. So the output of a perceptron is maximally 1 bit. Now, the memory capacity of a perceptron is the number of parameters. We just derived this based off McKay, and we can do that in bits, right? And now the maximum memory capacity of 2 perceptrons that are in parallel is additive. That also makes sense. If you take 10 megabytes of memory and another 10 megabytes of memory, you have 20 megabytes of memory, right? And if the memory looks at the same stuff, that's just how it works, okay? Now, more interesting, and this took a long time because there's an entire book on it from Leonard Tishby in 2012, is for us to realize that if you have deep learning sort of layers in parallel, that obviously there's something called the data processing inequality. That means you cannot create information. And this, again, was lengthily discussed by Tishby. And so what we need to say is that the maximum memory capacity of a layer of perceptrons, depending on a previous layer, is limited by the maximum output of that previous layer. This sounds complicated, but here's what happens. If I give you a 100 megabyte hard disk and 4 bits of data, do you have 100 megabyte of data or 4 bits of data? You have 4 bits of data, okay? So even though there's a lot of memory, let's say in a large layer, because the previous layer just gives you data, you don't have to consider that memory because it will never give you anything. It's like if I give you 100 bytes of information, that's 100 bytes. Whether you store that in a terabyte hard disk, it doesn't give you more information. And that's the same thing here. The output will usually limit what's coming into the input. And funnily enough, if you ever heard about the vanishing gradient problem, that's exactly the same issue, that when you go data processing inequality backwards as you do backpropagation, your gradient vanishes because you get less and less and less and less information to the first layers that actually need the most tuning. And that's why deep learners above a certain number of layers can't be trained. So let's do this practically, okay? This is actually very practical rules. And there's also an app, it's called TF Meter. that you should TensorFlow meter that we have populated as part of my academic work, where you can do this automatically. So let's all of these neurons here have weights implicitly at the input arrows and also a bias in the middle. So as we say, the number of parameters as of rule 2 equals the number of bits. Yep, this perceptron 1, 2, 3 can actually memorize 3 bits of a function, and that is of course consistent with the number of Boolean functions, because we can guarantee that 3 rows of a table can be memorized. If it's 4 rows, it may or may not work. If it's 5 rows, it may or may not work. The big point is we can guarantee 3 rows of a binary classifier can be memorized. Now, how do we go from a single to multi? Well, again, so now we have two perceptrons of 3 parameters each, and then parallel. So we have to just say 3 plus 3, and that gives us 6. And now, while we have another perceptron here that has 3 parameters, 1, 2, 3, we have to apply rule number 4, because while this thing has 3 parameters and 3 bits of memory, really it only sees the 2 bits of output. And so it becomes 2 times 3 bits plus the minimum of the 2 bits of output and the 3 bits of capacity. And obviously 6 plus 2 is 8. Okay, so this thing has 8 bits of capacity. Now we can go with deep learning, would be the same trick. So we have 1, 2, 3. 1, 2, 3 is 2 times 3. And now, which is kind of a little tricky, despite the fact that these are 2 outputs per neuron, it's both the same information, right? It's fire or not fire, both on the same lines. So despite the fact that this is sort of crossed over, it doesn't matter, because reality is there's 1 bit of information flowing into here and also into here, and 1 bit of information flowing into here. In total, it's 2 bits of information, 2 bits of output. So it stays the minimum of 2 and 6, which obviously is 2. And then the same happens again in the end, where you have 2 outputs, and this is the minimizer. So you end up with 6 plus 2 plus 2, which is 6 plus 4, which is 10. So you can see the interesting part here is that we really have information reduction as we go deeper, deeper, deeper into the layers. And of course, that's expected. In computer vision, they like it because it's kind of feature reduction, right? But that is basically how you get to the total memory equivalent capacity. So these 10 bits, this network here, as you have in front, is guaranteed to memorize 10 bits of a table, okay? Now, we don't want to just explain layered networks, right? We want to explain everything. So this is called a shortcut network. A shortcut network is actually something that has been invented very early, but it was recently reinvented and called ResNet. Okay. Now here's what's interesting. We can do the same math. So we have 1, 2, 3 bits that can be memorized by guarantee. And then we have 1, 2, 3, 4. And the funny thing here is that this thing is actually connected to the original input. And then this takes the input, the output also. So actually we have to do 3 plus 4. And this right there explains why resonance are so powerful, because they actually sort of informed, right? So you can think about this. If you go to a car dealership and you're not sure which car you want to buy, and you go back to a friend, but the friend hasn't seen the car, the information you give to your friend will mostly is the only thing your friend can use. But let's say you both go to the car dealership, right? So that means you both get the original input. Then your friend can actually give his or her true opinion, and you get them to a much better decision based on a lot more information. So I like this because this is basically the model of sort of collaborative decision, where you both look at the actual truth in the beginning. And yeah, it has a lot more power. It's 7 bits rather than 3 plus 1 would be 4 bits, right? So now we have to say, okay, fine, you talked me about memorization, but nobody wants to memorize. And you're right, nobody wants to memorize. But remember that memorization is worst case generalization. So all we have to do now is ask ourselves, where do we actually want to go once we know how much we can memorize? Where we want to go is we want to get to less parameters. We want to reduce parameters. And the way to reduce parameters um, is algorithmically, but what I'm going to say here is let's create a measure first of what the parameter reduction gives us, okay? And so we will define generalization as the number of correctly classified instances divided by the memory equivalent capacity. And you can immediately see that if the generalization is 1, then there's no generalization, because you basically have uh, the same amount of correctly classified instances that you could memorize. That means you have a lookup table. Congratulations, right? And then if you go below 1, you just have a really inefficient lookup table. And if you go above 1, the more you go above 1, the better it is, because that means with very few parameters, you can now correctly classify a lot more instances. And that means each parameter takes up way more than one prediction. And that means there's a high chance that if you see an unseen value of the same distribution, that will be done correctly. Now we have to also correct a little bit for the class balance. So we will know, obviously, if you have a balanced coin, then it's a 50-50 chance. Then each correctly classified instances is 1 bit. But if you had, let's say, an unbalanced coin, it would be 10-90 chance. Then obviously predicting each of them is less than 1 bit, and also predicting the ones that are 10% chance outcomes have a lot higher value than the ones that 90% chance outcomes. So what we do is we multiply the whole thing to be able to measure in bits per bit. We multiply the whole thing by the Shannon entropy of the class distribution. Okay. And then there's another problem. Another problem is that what if our neural network or machine learner just is lossless compression? What if actually for some reason it's lossless compression? Well, then we're still overfitting. Okay. And now we will actually, part of Brainome's core work is to find all these constants where we are actually overfitting, to find out how to actually figure out when it's overfitting and when it's not. And so I'm not going to give you those. They depend on a bunch of, it's also, the derivation of those is not so easy. They depend on a bunch of things, including the class balance and the number of classes. So now that we have a measure of generalization, we could do the following. We could take your table of input data, column 1, 2, 3, 4, 5, 6, 7, and say, well, what if we just, out of the data, took the first column and then the second column, the first column against the training data, and then the second column against the training data, and the third column against the training data, and we picked the column that will give us the best generalization. Okay. And then what we go and we say, that's kind of cool. Why don't we take the one that gave us the best generalization and see what happens if we make it a tuple, right? So we take the first one and then we take a second one to it. And if the generalization goes up further, that would be great. And so we repeat that process sort of with the first one and then adding a second and maybe a third and maybe a fourth attribute until there's no more attribute to add that would increase the generalization. And this is how we do attribute selection. And if you think about it, the first time you go through, it's n attributes. The second time, it's n minus 1. The third time, it's n minus 2. And then it's n minus 3, and so on. So you end up with n times n minus 1 times n minus 2 times n minus 3 runtime, which is n choose 2 comparisons. And n choose 2 is bound by n squared, which is really nice because otherwise, if you just had to choose random subsets, it would be 2 to the power of n. And we can do all of this because we can measure generalization directly by measuring the memory equivalent capacity. And of course, if it's smaller, then the number of, again, the number of instances that we have in the table, then we can generalize. And all of this is done, by the way, without building a model. This can be done totally a priori by basically measuring things out, which I haven't gone into very deeply, but again, that's what we can do in 30 minutes. So I know this is a dense talk, and there's a bunch of references that I would like to have people look at. One is David McKay. The other one is you should just take a look at the original paper from Shannon just to understand the communication model. But also, if you Google me and you see the memory equivalent capacity of neural networks, it's the paper called A Practical Guide to Sizing Neural Networks, which explains all of these sort of ideas with different architectures in detail. And then also on the Brainome website, we have a bunch of instruction videos, and there's also a machine learning experimental cheat sheet that gives you a lot more sort of in-depth on generalization and on sort of the conceptual way. So all of the stuff that you see here is directly derived from the definition of intelligence, and sort of from the original sort of philosophical way of how, first of all, psychologists and sociologists think about it, and then applying it to the machine, and then applying the math, and going down. So it's, we try to do a very systematic, scientifically based approach uh, for machine learning that will and does lead in the practical product um, to something where you can just measure and have the confidence before you build something, where it's not just try and error. Yeah, and with that, I want to just open for questions.
Great, Gerald, thank you so much for that very detailed and helpful presentation. I want to invite everyone who's attending to put more questions into the Q&A channel. We do have a number of questions here that are queued up, but there's absolutely time and space for more. So if you are sitting with a question, just pop it into the Q&A channel and we'll get to it in a minute. There is an initial question here from Rajesh. He would like to know, he says, it seems as if you're saying that there's a way to measure learnability of data in a way that's specific to a particular type of machine learning model. Is that correct? And if that's so, then what types of models does it work for?
Okay, so first of all, it works for every model. And that may be surprising, but every model can overfit. And that means every model has a memory equivalent capacity. Now, where you get to the memory equivalent capacity, that is work, right? Just like how we had to figure out for neural networks that is like circuits. But I'll give you another example, which is kind of easy, which is the decision tree, right? So the memory equivalent capacity of a decision tree is obviously the depth of the perfect tree, right? Because each branch is a bit, right? So if you have 4 branches, the tree is perfect, and it's 4-bit of memorization that this tree can do. Um, and as you prune that tree, you get generalization, right? Because now you don't have to go through all branches. And so the interesting part is that this is true for magnets. And you might be surprised, what is the memory equivalent capacity of a magnet? Well, it's the Ising model. The point is, your hard disk has a memory equivalent capacity, right? So because that's what you actually see when you ask your operating system how much memory you have left. Because guess what? Your operating system tells you like 1 terabyte of a hard disk, but the reality is that how it's internally stored on the hard disk is a very interesting question that's only mostly known by the manufacturer of the hard disk. And so we do the same thing here with neural networks, where we say, well, we know it depends on the topology and all of these things, which you just saw. But the point is, ultimately, all networks, there's a bunch of networks maybe of different topologies, but ultimately they can have the same memory equivalent capacity. And so we can now compare all machine learners by their memory equivalent capacity. And the interesting part is how does it behave in terms of adding a parameter? Which parameter adds actually memory equivalent capacity and which parameter doesn't? So for example, in a deep learner, if you add a bunch of parameters in the last layer, you already know that we're bound by the minimum, right? So adding a lot of parameters in the last layer will just increase your training time. It will not do anything to your memory equivalent capacity. It doesn't help. So it's a measure of efficiency as well. Now, in general, as I say, every model has a memory equivalent capacity, but Brainome will basically just focus for the first product that we have, Dimensions, only focuses on decision trees and neural networks because that's what we work on. But we think about adding XGBoost, sort of more random forest type of things, Gaussian mixture models, to that, where again we can also come up with a memory equivalent capacity. And so now the second question, I think, was how does it make the whole thing specific to the machine learner? Well, so the trick here is we have Shannon entropy, right? So Shannon entropy gives us the sort of expected memory capacity needed to store something, right? And so the trick here is when you have that, you can calculate that just by calculating the Shannon entropy. Is a measurement. You don't need the model. And so that's the expected absolute minimum. And now we say, well, okay, to reach that using a neural network, it would be that same memory equivalent capacity. Or to reach that using a decision tree, you would have to match that same memory equivalent capacity. That's how things become specific to models. Hopefully that makes sense.
Great. Excellent explanation there. Um, there's a question here from Kareem. He says he saw a previous webinar that Brainome put on, and that in that one, we talked about how measurement was used to do attribute selection.
Mhm.
And he's asking, how well does it work?
Well, try for yourself. So, how well does it work? So we'll find the attributes with the best generalization. So, how well depends obviously on what your goals are. So, um, you may go through a data set and we find like one or two attributes that generalize really well. That means you get like one or two neurons or one or two if thens in a decision tree. But then you get near best guess accuracy. And it's like, oh, what do you do? Well, what we do then is in these algorithms, we give you a k parameter. We can actually say, okay, look, don't stop when you don't generalize more. I'm okay with just basically generalizing less, but adding to the accuracy. And then what the algorithm does, let's say you give it rank 5, you say, I want 5 attributes by guarantee, but 3 was what came originally out. Then it will add 2 more that are sort of, yeah, we're reducing generalization, but we're reducing generalization the least. And of course, by doing so, you'll implicitly increase memorization. That means you implicitly increase accuracy, and that helps to actually tune that, to go onto that trade-off between generalization and and memorization, which you want to do.
Thank you very much. Uh, Robert has a question for you as well. He says, I don't understand why you think you need an upper bound like memory equivalent capacity. Some of the best models out there are much bigger than what the memory equivalent capacity would be, and they perform really well and they do really interesting things. So why do you think that this approach is better?
So I put it like this. Remember when you take the example from the last seminar, which is like 2, 4, 6, 8, 10, right? Now we all know the rule is +2. But the rule, which is implemented by the model, could also be plus zero point 0.1, plus zero point 0.1, plus zero point 0.1, plus zero point 0.1 until that term reaches 2, right? And obviously now you need 20 of those plus zero point 0.1s, which is much longer than the input, which was just 2, 4, 6, 8, 10. Now, it does generalize, though. It does generalize to a validation set because, again, just because you have a complicated calculation that is correct doesn't mean you have an incorrect calculation. A complicated calculation that is correct is still correct. So a complicated model that is correct is still correct. But here's 2 problems. One problem is we want to remember, be part of the scientific process. We want to get the formula out if we can. So we don't want complicated formulas. We want easy formulas. But even going further, as an engineer, I have no way of knowing whether your thing is actually generalizing well or not, other than saying the only way I can guarantee generalization is by using the least amount of parameters. And that has a lot of beautiful side effects too. For example, we know that by making the model more general, that means less and less and less parameters, we reduce the number of adversarial samples, which is also consistent with Occam's razor. And also there's a bunch of stuff that just makes the engineering easier. So yes, you can by luck find a model that does it despite the fact that it's huge. But also, let's save compute, let's save training time, let's not go with luck. There's a reason why cars have 4 wheels and all of them have 4 wheels and not just 25 because, hey, why not, right? So ultimately, it's a matter of streamlining and resource constraining as well.
Great. Thank you. Danielle is asking, why haven't I heard about this before? I don't see it at Google or Amazon or Microsoft or any place like that. What's going on?
Well, first of all, this is the work of 3 years of work of research. And meanwhile, I looked at related work, and you see all the related work that I also look at. I haven't seen that, full stop. I think it's we found that it's our invention. Number two, they have a different business model. They actually don't have any incentive to go in and make that invention, because they sell you CPU time and GPU time, and they want to actually to try and error, because the more you have to try and error, the more money you spend on their cloud. While I think that's insanity, we decided, we don't have that model. In our case, we license out software that just does the job really quickly, really fast, and very reliable. For me, that's just engineering, and the way it should be, to be frank.
Great. Got it. And then we do have one more question. I will invite everybody once again, if you have any remaining questions, to pop them into the Q&A channel.
Mhm.
But the last one I have here is from Ahmed. And he says, I often work with highly unbalanced data sets because I work in the fraud detection space. So I've typically got, 98% in a majority class, and then maybe a couple of small classes with under 1% of the data. Um, would these approaches work for that kind of data set? And if so, how and why?
There's actually one more question also from Anton Petrov, if you look into QA. But so Anton, stay, because we're going to answer your question, okay? But to answer this question, this approach works better. The reason is that if you measure accuracy in the number of correctly classified instances divided by the number of um, total instances, then you totally disregard the fact that 19, if you have a 19, let's say you have 99 instances that are class 1 and 1 instance that are class 0, then the best guess is 99% correct, right? So, however, those 99 instances don't give you any information. Information is surprise, right? The more surprise you have, the more information you get. The more information you get, the better it is, right? And so the major trick here is that um, by taking into account the information content of each instance, you actually make it so that the 99, yeah, that's fine. Really, what we need is the one, right? The one exception. And obviously, what we need is all of them. But the point is that you can probably trade off a bunch of the 99s for the one, to have the one. And in regular machine learning, by just optimizing for the number of correctly classified, you'll just find the 99, and the one counts the same as all the 99 that you're not interested in. And so yes, this approach works a lot better, because we actually inherently look at the uncertainty reduction, aka information, that we get by predicting a certain outcome.
Great. Got it. Anton, I actually don't see your question in the Q&A channel,
Okay, I
so
can
I'm
I can
going
read
to,
it.
I'm,
Yeah, I can.
okay. I also, I made it possible for Anton to talk. If he wants to unmute and ask his question himself, he can.
Okay, sure, I can read the question.
Thanks.
So, all right, I was curious about how are you doing with feature engineering step? I mean, in our typically training data set is outdated. It might be not relevant because it's historical data, and those patterns which happened in pre-COVID era, they won't repeat itself in the future. And by using feature engineering, we always try to encode our domain expertise in our data, and we often see that those features encoded by ourselves, they're crucial during the modeling phase. So how do you deal with it in your approach? Thanks.
So 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 there's a theoretical answer and a practical answer. The theoretical answer is, you doing feature engineering is nothing else but sort of doing layers of neurons by yourself, right? So instead of taking the raw data and then have to train layers of neurons to sort of create features first before we go into decision layers, you do that by yourself. And by the way, I never saw anything wrong with that. The practical answer is Brainome Dimensions is actually really good for feature engineering. Okay, this is probably we'll explain that more in the 301 talk. But the interesting part is, because you can measure before you build, Right now, the feature engineering process is you have some features and then you build a model and you hope it works, right? And also, if it doesn't work, you don't know if it's my hyperparameter tuning or did I do something wrong. Now with Brainome Dimensions, you take your data and you measure out the learnability for a neural network, the learnability for a decision tree, the generalization progression, the risk of overfit. All of these are things that you can measure in seconds, even for rather large data. And now you can play around with your features and see, okay, which ones would give me the best learnability and the least risk of overfit. And that helps obviously a lot. Um, and so I invite you to actually try this. We have this demo. It's on brainome.ai. And if you click on demo, you can also upload, let's say, a small data set of your own and try it.
I'll also add, Anton, that last Thursday we did a full webinar on how to do data feature engineering and data preparation using our measurement approaches. So that's a video of that webinar has been archived, and you can find it on our website and have a look at it. If you have any questions about this, please just email support@brainome.ai. So I'd like to say thank you very much for coming in and seeing us today. And I want to just remind you that we're going to be having some more webinars coming up. And the next Core Tech webinar is Tuesday, 10 a.m. Pacific next week. We're going to be Gerald's going to be back, and he's going to summarize the math that we went over today and the approach in general, but he's going to go through in detail a bunch of use cases and examples. So I highly recommend that you come and see us for that. And then this Thursday, just 2 days from now at 10 a.m., we're going to be doing another benefits and applications webinar about the kinds of problems where you need to quote unquote find the needle in the haystack. These are data sets that are very broad, have tens of thousands or more features, but only a few rows. And what you're looking for is which are the attributes that are creating the outcomes. These kinds of applications are in genomics and bioinformatics and food design, those kinds of applications. So you can join us Thursday to hear about that in detail. I encourage you all to, if you haven't done so already, go over to our website and try the demo version of the software. You can also sign up as a registered user and get some additional power, some additional features and parameters available to you. And if you want to come back and see some more webinars, please just go over to our events page on the website and sign up. Thanks very much for being with us today. We really appreciate your time. And please, if you have any questions or any follow-up, just email support@brainome.ai. Thanks and have a great day.